All right, today we're talking about Chapter 2, Section 4, Applications, Uninhibited and Limited Growth Models. I think, actually. I think I do this every single time. It's because the class before this one, I have to snip them individually. This whole darn thing. Current page. Alrighty, so exponential growth. If we consider the following function, f of x is equal to 2 times e to the 3x, and if we differentiate, we know we take the derivative of the exponent and multiply it by the function. And of course, f of x is just simply this, right? 2e to the 3x. I know it's written a little different. It's written a little weird, but it is a true statement. And it's just kind of getting you used to the notation. Instead of just rewriting 2e to the 3x, it was just rewritten as f of x. Graphically, this says that the derivative or the slope of the tangent line is 3 times the function value. That makes sense. Functions of the form f of x is equal to ce to the kx is very important, and we're going to be doing that a lot, at least for the first two examples, I think. Have the property that the derivative is a constant multiple of k of the function. So our theorem that we're starting off with here, and I'll do it in a second. A function y is equal to f of x, it satisfies dy dx, right, the derivative of y, which is the name of the function, over the derivative of x, which is the variable, again, remember that notation, is going to be equal to ky, or f prime of x is going to be equal to k times the function, right, again, k is just some constant, if and only if we have y is equal to ce to the kx, or, in other words, again, f of x and y, as we've mentioned before, are virtually interchangeable. They're meaning the same thing. The function at x is indeed y. And it's going to be equal to ce to the kx. And again, I know that doesn't mean too much to you until you actually get a nice hearty example. So let's pop one of these up. Bring the theorem along with me for this example. I think we can put two examples here, because example 2 I was just going to snip, yeah. So we'll just keep that there for right now. Alrighty, so example 1 reads, find the function that satisfies each equation. So if we read this, it is dA, again, the d's are just the derivative, right? The derivative of a with respect to the derivative of x. So that is just the name of the function. dA is the name of the function, and then the x is the variable. Once again, we need to find the function that satisfies each equation. Well, for a, if we follow along with what we have over here, all right, we're in the form dy over dx is equal to ky, right? Can we see that the numerator would correspond to dy, the denominator, well, it's dx, and then we have 5a corresponds to ky. So with that said, our function would simply be let's do the f of x instead of the a. So it would actually be a of x. Sorry. So we would say a of x. One moment. Don't have a good base for my computer right now. Right, so a of x, all right, is equal to what? All right, so I'm following along with this right here. Well, not really. I'm actually following along with this one, right? So we're going from the top left and we're converting it to the bottom right, essentially. So my function name is a, so I say a of x. Well, what is a of x? Well, a of x is equal to c, all right, some constant, times e raised to the blank x, or yeah, blank x. Well, blank here is just going to be 5, right? Because again, we're going from here. So we're going to say 5x. And that's it. So we just followed along. We know that we have we can convert a statement of dA over dx equal to 5a. We can convert that to ce to the 5x. And that's a Let's move this over a little bit. Okay, there we go. And then b works kind of the same way, right? Instead of a of x, what's the name of my function? My function name is p. So it's going to be p of what? Well, it's not going to be x because we're talking about with respect to t down here, right? So it's going to be p of t. And that's going to be equal to, again, following the theorem over here there to the right. I got hair on my screen. It's just going to be equal to some constant times e to the uh, we're raising it to some exponent, kind of follow along here, or our theorem to the right. Well, it looks like it's going to be raised to just some kt, right? Because we have k located right here, and that's it. That's just uh, changing it from one notation to the other. And honestly, I feel like, well, especially on the homework, once you know what you're doing, it took me about 6.5 minutes to go through this problem. You'll be able to do this in like 10 seconds. And example two is just so easy. I'm just going to just snip the whole darn thing. There's not really much to it. And we're going to put it right here below. All right, so it reads solve the differential equation, and we have f prime of z is equal to 0.06 times f of z. Well, we know that the solution is just going to simply be CE, right? Same thing, CE, so see here, CE, raised to the, and we see our derivative there, 0.06, which we have here. And again, 5 for A, K for B. Here's 5, here's K. And then that's where the 0.06 goes. And then, of course, my variable Z. And again, super duper easy. Like I said, now we're at 7.5 minutes, but on the homework, you're going to be done with that very quickly. But all that is needed to know what we're about to do now. Uninhibited population growth. So, um, well, heck, I mean, we've lived through the coronavirus or COVID-19, and we've seen all sorts of projections and things like that. And where do these projections come from? Well, they come from something like this: uninhibited population growth, and the population here would be the virus. Well, we have the differential equation. Sorry, dp over dt. Again, that's equal to kp, or everything we just talked about. All right, this is the model of uninhibited or unrestrained population growth. So in the absence of uninhibited or stimulating factors, a population normally reproduces at a rate proportional to its size. Now I say this because last year, I remember when it first when COVID-19 was first popping, there was a projection that something like 150 million people or something. I might be off on that. I don't know because that's almost half the population of the United States. But something extraordinary like that. Um, Almost half the people in the United States would die of COVID-19 if we didn't do anything. If we uninhibited the growth of the virus. And then so the CDC comes out. We're talking about masks, we're talking about social distancing, we're talking about lockdowns, and now we're talking about vaccines and stuff. We're trying our best to inhibit the growth of the virus, and so this is kind of an idea of real life situations that we've seen of uninhibited growth, and then we inhibit it. But again, sorry for the tangent there, but we've seen some nice real life examples here. The only function that satisfies this differential equation is given by our function that we've seen already, where t and k is the rate expressed in decimal notation. All right, note that p of 0, right, when we plug in 0 for t, we simply just get the constant. So therefore, c represents the initial population, which we will denote as p naught. Population, p, and then the subscript 0 means naught, N-A-U-G-H-T, I believe, which just basically means the beginning, right? At t naught is initial time, at v naught is initial velocity. Well, p naught is initial population. And I think, let's see, I might have to, okay, we'll snip this. Can't remember if I should probably snip the equation or not. So we'll put this right next to our uninhibited population growth here. Ready? So we have our graph here, and this is just basically what an uninhibited population growth looks like, and that's why like I said, the the forecasted death rate of COVID-19, if it was uninhibited, it would have just skyrocketed. Well, uninhibited, and half of Americans would die from it if we didn't inhibit it. But of course, obviously, many steps are taken. Uh, and let's see. Oh yeah, this is important. The constant k we're going to call the rate of exponential growth or the exponential growth rate. And k, I think it's actually given to us a couple times. But K, in many courses, especially if you've had my pre-calc course, uh, the exercise that we do mainly is to find K. But with that said, let's just jump in and just see what we're going to do here. All right, so absolutely more compounding interest. All right. Compounding interest in this course is like quadratic formula in college algebra. We cannot get away from compounding interest. So anyways, suppose that P naught in dollars is invested in the von Neumann high yield fund with interest compounded continuously at 7% per year. That is, at any point in time after T years, the balance P in dollars per year is growing at a rate of dP over dt, that's equal to 0.07 times P. Okay, so that's a lot of words there. A, find the function that satisfies the equation. Write it in terms of P naught is equal to 0.07. Well, this is just basically the first exercise we did, right? The first two, I guess, since we're on example 3. One moment. Never mind, false alarm. Thought I had to sneeze. Okay, yeah. So find the function that satisfies the equation. Write it in terms of P naught is equal to 0.07. So we're going to have our equation. Our equation is going to be looking at our derivative here. We know that we can see that the function's name is P. Okay, we know that the function name is P, so there's that. So we're going to write P of, okay, well, what is the variable that we're using? Well, that's going to be down here. So we have d of t, so P of t. That is the name of the function. Right, what is that equal to? Well, going back to the previous slide, right here, we see at P of t, it's equal to the initial population times e raised to kt power. So we're going to do that. So we're going to have the initial population, P naught times e raised to some kt power. Well, we are told, yeah, we are told what k is, which in this particular case is 0.07. So 0.07 t. And of course, this particular equation is kind of what we saw what we saw in the first two examples, right? We have the constant c. Let's see, go back here. Example 1. We had our constant 5, and that's what we used for the k. We have our constant k, so we use for the k, and of course our variables are same. Okay, so a here is nothing different than the first two examples. So that was it. We need to find the function that satisfies the equation. We did that. Easy stuff. B is just going to go back to college algebra. It reads, suppose that $10,000 is invested. What is the balance after 1 year? Okay, so we're told that $10,000 is invested, so that's going to be, we're going to put that in place of our P naught, okay, because that, going back up here, it says suppose P naught in dollars is invested. Okay, so we're going to put 10,000 for P naught, and then we have, it's asking what is the balance after 1 year, so the t is going to be 1. So my equation is just going to be 10,000 times e to the 0.07, and then times t, and once after 1 year, so it's going to be 1. And then we just have to do that arithmetic. And some behind the scenes calculator work. 10,000 times e raised to the 0.07. So $10,725. Doesn't want it in cents. Let's put it below. So $10,725.08. All right, so $700 after a year. Not terrible. I mean, 7% a year isn't that bad, to be honest with you. Especially if the market on average does what, like 11%. That's actually pretty good, especially if it's a nice, safe interest rate account. But anyways, so that's B. Now C, if $10,000 is invested, how fast is the balance growing after T equals 1 year? Alrighty. So it's one thing to know how fast we're growing at T equals 1 year. So if we want to know how fast we're growing, it's one thing to know the rate of change, right? So in order to figure out the rate of change, then we must take the derivative. So we're going to take our function. All right, so P of T, and that's and our function is if 10,000 is invested, so 10,000 is invested. All right, and then we have e to the 0.07. We're not going to put a 1 for t just yet, because we'll put the 1 for t after we differentiate it, right? Because it's one thing to know how fast we're growing at t is equal to 1 year. So we must take the derivative here before we actually compute that. So we're going to write p prime of t. Okay, well, what is p prime of t? Let's just do some. I'm not going to say mental math because, well, I mean, actually it is mental math. This is pretty good mental math here. But let me see. It says my internet connection is unstable. So if I lost you, that kind of sucks. All right, so 10,000. So if you recall, what we're going to do is we're just going to take the derivative of this, right? And because it's first times derivative of second plus the second times derivative of first. Well, the first times the derivative of the second there. No, that's too much. Never mind. We know that for e raised to 0.07t, we just keep what I wrote in the red box, but then we differentiate what the exponent is. Well, the exponent is 0.07t, so it's going to be times 0.07. So this is going to be my equation essentially, right? Well, now I'm going to take this and multiply it by 10,000, right? Well, 0.07 is just simply 7%, isn't it? So that's why I said we could do mental math here. Well, what is 7% of 10,000? Well, that's just going to be 700. Okay, so my derivative is going to be just simply 700 times e raised to 0.07t. And then from here, well, we did it. We got the derivative. And what is p prime of 1? And we'll put that over here. P prime of 1. We're just going to do some more calculator work, but of course we know that we're looking at this, and so if I want to find p prime of 1, then I take the t and put a 1 there for t, and that's pretty easy. It's just going to be 0.07. So anyways, what is 700 times e raised to the 0.07? It's going to be 750. 0.76. We'll just do 750. So it's growing at a rate of $750 per year after 1 year. And of course, that's going to, as we move up, we're going to be growing much faster, or exponentially faster. Yes, yeah, they did decimals, which makes sense. I just ran out of room. And really quickly, before I do continue on, maybe those that are watching this on YouTube, or you might be saying, well, you have room over here, right? You have room right here to write it, and that's true. But there's these gray lines here, and that's what I try to stay in between, because whenever I convert this to a PDF, everything on the outside of those gray lines gets cut off. So that's why I didn't want to put anything there. Again, you didn't ask, but there it is. So anyways, more word problems, and again, I I enjoy word problems. I think they're the best way to demonstrate the uses of what we're doing in math courses, as opposed to mindlessly factoring your brains out. And hopefully, maybe by the time you get done with this course, you're like, you know what, word problems aren't so bad. But at the same time, I got bad news for you. This class has a lot of word problems because, well, as the name of the course implies, it's applied calculus. So physical science. In 1971, Intel Corporation released the Intel 4004 microprocessor, which held a measly 2,300 transistors. Since then, the number of transistors on a microprocessor has been growing exponentially at a rate of 0.35 or 35% a year. So that is, we have dp over dt is equal to, sorry about that, dp over dt is equal to 0.35 p. So where t is the number of years after 1971. We need to A, find the function that satisfies this equation, assume that P naught is equal to 2300 and K is equal to 0.35. So with that, it's pretty easy. We don't have to do too much there because it's all given to us. So A, we need to find the equation. So again, in order to find this equation, let's first look here. Okay, well, dP, that tells me that the function's name is P, over dt, which tells me that the variable involved is t, so p of t is equal to, all right, well, again, we have the population, p naught, so that's going to go into place of the c that we did from the first two examples, I think, so 2300 times e raised to the kt. Well, we're told what k is. K is 0.35, and then t. That was pretty easy. B, estimate the number of transistors on a microprocessor in 2025. And again, this is just going back to college algebra. This has nothing to do with calculus, but there's nothing wrong with being able to remember to do this. So it says estimate the number of transistors on a microprocessor in 2025. So if we're starting in 1971, then all we have to do, if we're looking at this, just this side of the equation, there's only one variable, and that's just t. So all we have to do is plug some number in for t. Well, 2025 is how many years after 1971? So it's 54. So we're just going to plug in 54 for t. So we have 2300 times e raised to the 54 times 0.35. Holy smokes. Is that right? I think so. Okay, so let me just double check here. I did everything right. They use scientific notation. Okay, no big deal. I'm gonna write just the whole number out. 371 444 444 168 and 047. Okay, so 371 billion. That would be the estimated number of transistors on a microprocessor in 2025. I wonder how many there are right now. I'll check it out after class. Right. Well, that was B. Now C reads, find the rate at which the number of transistors on a microprocessor is changing in 2025. And again, all we have to do here is take my original function, differentiate it once, and then plug in 54 for t. So p prime of t is going to be equal to, well, again, It is first times derivative of second, blah, blah, blah. I say blah, blah. Why did I say that? I shouldn't have said that. Sorry about that. First times derivative of second plus the second times the derivative of the first. But we know that the derivative of 2300 is 0, so we can just simply take the first times derivative of the second. So we take this, and then we put the 0.35 there, and then you take the 0.35 and then multiply by 2300. Again, the same thing we did on the previous example. So we'd say 35% of 2300 is 805. So we say 805 times e to the 0.35t. Okay. Well, what is p prime of 54? We plug in a 54 for t, and we have 805 times e raised to the 0.35 times 54. Golly, these numbers are humongous. Okay, so 130 billion. So our transistors in 2025, they are increasing at a rate of 130 billion per year. And of course, that is going up every single year, but in 54 years, that's the rate of change. Oh, that's incredible. One moment. I'm gonna make a note to find the number of transistors. I just want to know how accurate that is. All right, so that's that, and we're gonna do comic book values. I guess I'll include the source. Right? We always have to include the source. Alrighty, excuse me. So example 5 reads, a 1939 comic book with the first appearance of the Caped Crusader Batman sold at an auction in Dallas in 2010 for a record $1.075 million. The comic book originally cost 10 cents. Using the data point 0, 10, and 71, $1,075,000. So real quickly, this data point, these data points are just simply points on a graph. So in the past, we have just simply plotted points on a graph. Well, these points now mean something. At x equals 0, my y is 10 cents. And at x equals 71, my y is $1.075 million. And these are now points that we can plot on a graph, and we can see that it's, I don't have to graph yet, and we can see that it is exponential. So we can model the increasing value of the comic book. The modeling assumption is that the value v of the comic book grows exponentially as given by dv over dt is equal to kv. So find the function that satisfies the equation. Assume that v naught is equal to 10 cents. Well, again, this is just the same equation that we've been doing in every one of these problems, I think, today. Right? So again, what's the name of my function? Well, the name of my function is v. What's the variable being used? Well, it's t. Okay, and then it's equal to v naught. Well, we are told that assume v naught is 10 cents. So we can assume that v naught is 10 cents. We put 0.1. We'll just put 0.1. That's 10 cents. Well, no, let's do, if we're talking about cents, let's just put 0.1, 0.10. And then it is times e to the, we're not told a k, so that's that. Okay, so that's the function we have starting out, right? And we're told we need to find the function that satisfies that equation. Well, this function here has two unknowns on the right side. What I mean, right over here, we have two unknowns, right? One of the unknowns is k, and one of the unknowns is t. That's slightly unfortunate, and it's slightly unfortunate because on the previous example, you see we were given k. So how do we solve for k here? And again, this is just going back to previous math courses, pre-calculus, college algebra. We have to find k in order to proceed with this problem. Well, we are told two data points here. One of them is at 0, when x is 0, y is 0.10, and when x is 71, y is 1.075. All right, now that would be xy on an xy coordinate plane. Well, in this particular case, we don't necessarily have an xy. We have t and v of t. Okay, so real quickly, let's do this. We have xy. We know xy. We also know that could be thought of as as x and f of x, right? Well, for this particular function, we're given a t and then v of t. Okay, again, the same xy that we're familiar with, except now it's in terms of t v of t. So what we have to do is we are given t's. All right, the t is basically the first part in these data points, 0 and 71, and v of t is the second part, 10 cents and 1.075 million. So I'm going to choose one of those two to plug into this original equation to find out what k is. Well, the option should be abundantly clear to you, because if you have the option to use 0 in any equation, you use it, because 0 makes things so much easier. So we're going to say 0.10. Okay, that is what v of t is equal to. Excuse me, 0.10, and that's equal to 0.10 e to the, we don't know what k is yet, but t is going to be 0, right? Because that is at time 0. So doing the arithmetic here, we can see that solving for k, we get that goes 0. Maybe I shouldn't use that actually in second thought. Okay, never mind. Scratch that. Okay, so real quickly, well, let's just bring that back actually. Let's bring that back actually. I did say that if you have 0 available to you, you should probably use 0. Okay, and that is honestly mostly the case, except for, well, this problem. If I'm solving for k in this particular case, I see that k times 0 is 0, and that just takes the k away. So I can't really solve for k, can I? So what I'm going to have to do is not use that first data point and actually use the second one, which isn't as fun, or rather as easy, but it has to be used. So that was actually a pretty good exercise, and it's not always the case. It's not always the rule, right? So anyways, v of t, and now we're going to do v of t is going to be 1,075,000, and that's equal to 0.10 e to the k, and again we're looking for k, and then my t here is 71. Okay, and again I'm looking at this data point here. So from here now I have to solve for k. Okay, so we're going to divide both sides by 0.1. What is, well, let's see, we'll just do that. 0. Okay, so we divide both sides by 0.1. We end up with 1,075,000. So 10 million. I knew that. I don't know how to put that in a calculator. Okay, and then that's equal to e raised to the 71k. k. All right, well, how do I figure out what k is? Well, we did this before in a previous section. We need to take the natural log of both sides. So if we take the natural log of the left side, we have the natural log of 10,750,000, and that's equal to e, or rather, natural log of e raised to the 71k. Okay. Well, we know from our power rules that I can take the 71k and put it out in front of the natural log of e, and I also know that the natural log of e is just simply 1. So this turns into, and I'm just going to go ahead and write the whole thing out so we're not skipping steps here in case you do look at these notes. We just end up with 71k. Okay, and then from here we're going to divide both sides by 71. So the natural log of, oh my goodness, this is 10,750,000. Hope that I did that right. Yeah. And then divide by 71. Well, that's not a terrible number. So we're going to end up with k is equal to 0.23. 0.23. Alrighty. So 0.23, and well, the textbook goes to 3 decimal places, so we'll just go ahead and go with 3 decimal places. They did 228. Right. I still hadn't actually wrote the function, so let's actually go ahead and write the function. So the function, all right, to actually sum up a, since we've actually found k, is going to be v of t is equal to 0.10 e to the k, which is 0.228, and I ran out of room. Let's try that again. So v of t is equal to 0.01, 0.1. We're just going to put 0.1 instead of 10 for space. 0.228 t. Okay, so that's officially my equation. That officially is the function, rather, that satisfies that equation. So now we get to go to b, and hopefully b is not as bad. This is kind of unfortunate that I have to go to the next page to snip the actual problems here. Hopefully I can fit B and C on this one page. That's A. All right, so B, we want to estimate the value of the comic book at the start of 2025. Okay, that's perfect. So what was my equation? My equation was, let's go ahead and snip that over here. So V of T is equal to 0. Times e to the, I think it was 0.228t. Okay, pretty sure that's right. Yeah. Okay, so that's my equation. So we need to estimate the value of the comic book at the start of 2025. Well, all we have to do is plug in an appropriate t for the start of 2025. Well, 2025 is 61 plus 25 is 86. So 86 years after 1939. So we would simply just write v of 86 is equal to 0.1 e to the 0.228 times 86. And that is equal to Holy smokes. It's a lot of money. Okay, so it is 32782,811. So $32 million. So if you were to base the value of this comic book exponentially, then in 2025 it will be worth 32 million. And of course, if somebody bought this comic book in 2010 for a little over $1 million, 15 years later they could sell it for $32 million, so they can get $31 million of profit. Now there is a problem with that. And I'm just going to put this into my calculator here. Let's do 200 years after 1939. Okay, so 200 years after 1939 would be 2139. So I'm just going to replace the 86 in my calculator with a 200. And holy smokes. Okay, so the number I get here when I replace it with a 200 is 6.36, and then we have e to the 18. And what that means is we're going to take 6.36, we're going to move this decimal 18 places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This is a pretty good exercise, a pretty good segue into the last part of this lecture. So this is how much? Let's put it in red actually so I can differentiate here. Okay, so this is million, billion, trillion, quintillion, and I don't know what the number is after quintillion, but in 200 years, this comic book will be worth 6.36 whatever is after quintillion, and that just doesn't make too much sense, does it? How could a comic, I mean, especially, 200 years from now, that number might exist, but it would definitely be a combined GDP of every sovereign nation in the world. It would be worth more than that. And that doesn't make too much sense, does it? All right, so that's where exponential growth models kind of break down, is at the extremes. But keep that in mind as we segue I'm pretty sure after this example, into the limited growth. So anyways, at what rate in dollars per year is a comic book increasing in value at the start of 2025? So again, all we have to do here is take our function and differentiate it. Take our function up here and just differentiate it. So we're going to have v prime of t is equal to, well, I'm just going to differentiate that function right now. So what is 0.228 times 0.1? It is 0.0228. So 0.0228 times e to the 0.228t. So that is the first derivative. And we're wanting to know at what rate in dollars per year is the comic book increasing. So we just have to replace that t with an 86. So v prime of 86 is going to be equal to, oh my goodness, okay, so 0.228. Okay, so it looks like it is increasing at a rate of 74481. It is increasing at a rate of $7.4 million per year. And again, that's just at 86 years, and if it's exponential, it should be growing a lot faster the next year. Now we're going to get to limited growth models. So as I showed about a comic book, the comic book's value in 200 years will be worth more than all the economies in the world put together. That doesn't make much sense, and that's where models of limited growth comes in. And models of limited growth, like exponential models, also have limiting factors to it. But we'll see examples of how it's good. So models of limited growth, we've seen that the growth model, P of t, applies to unlimited or unrestricted growth. However, there are often factors that prevent a quantity from exceeding some limiting value L. One model of such limited or restricted growth is our function here, which is called the logistic equation or logistic function. Let's see. An important thing here is L in our equation is called the upper limit or the limiting population. The rate of change of the population is directly proportional to the population P and to the remaining room for population growth L, our limited growth, minus P, which is again population. So this is our function, and good news, I don't think you have to actually memorize this. Everything I looked at, it's actually given to you. So wouldn't necessarily hold me to that, I guess, but that's that. So let's put a limited growth model example to the test here. And again, as you can see, it's given to us, so I'm not going to have to snip it over. Alrighty, so example 6, Dish Network's revenue R in billions of dollars T after, Dish Network's revenue is R in billions of dollars T after 2008 years. It can be modeled by the logistic equation given here. So the first example, again, college algebra, nothing extraordinary here. We just want to find the revenue in 2023 and in 2020 and in 2023. So all we have to do here is replace T with some numbers, T years after 2018. So 2020 is 12 years after, and 2023 is 15 years after. So all we have to do is find R of 12 and R of 15. So R of 12, oh gosh, I really don't know if I put that in my calculator, but it is what it is. And R of 15. Here we go. One moment, it's going to take me a hot second here. Okay. And really quickly, I'm going to go ahead and, because I feel like, again, many times, and I don't know if I did it in this class or the previous class, I did it, I mean, it was a user error with the calculator. And that happens, but for me, here's what I put into my calculator. 0 point, not 0, I put, all right, one moment. All right, so I put 31.95, and then I did a division symbol, and then I put another parentheses, 1 plus 1.759 e caret, and then I put this in parentheses, 0.0596 times 12, and then close that parentheses and close that parentheses. So this is what I put into my calculator. I'm just overly redundant with parentheses. Like I did not necessarily have to put the parentheses right here in the numerator, but I do anyways because if I have division symbols, I always like to make sure that my calculator knows this, all of this is in the numerator, all of this is in the denominator, and proceed from there. So again, I don't know if that's going to help you too much, but I'm pretty generous with my parentheses. So I have 17.17. Right? And that's after 12 years, and then after 15 years, it is 18.58. And so that's, again, simple college algebra problem. I just replace the t with a 12 and 15 respectively. And then B reads, find the rate at which the revenue was growing in 2015. Okay, so we have to figure out what, we have to differentiate this and figure out what the rate was, find the rate at which the revenue was growing in 2015. So, oh, this problem looks, this is not going to be fun at all, but let's move this down just a tad because we're going to use all that beneath it. Okay, so B, we're going to find r prime of t. We have to find the derivative before we find out how fast it was growing, or it would be r prime of 7. So we're going to have to do the quotient rule here. So low d high, so low is 1 point, I'm sorry, 1 plus, am I going to run out of room here? I don't know. This is my low, 5, 9, 8. Oh no, this is awful. Low times the derivative of the high, and I don't even need to write that. What's the derivative of the numerator? Well, it's 0, so times 0. Low d high minus high d low, which is going to be 31.95 times the derivative of the low, which is going to be, all right, so I can differentiate these in groups. Well, the derivative of 1 is 0, so I have to include that. But I have to do the derivative of this. Well, that's pretty easy. I'm just going to take, again, like we've seen in the previous examples, I'm just going to take the derivative of e to the negative 0.0596 t, and the derivative of that is looks like, and then times the 31.95. So we're going to end up getting, and let me just, I'm running out of room here, so let me just go ahead and just write this all by itself because it make it prettier. It's going to be 3.35 times e to the, and let's move it down. Dadgummit. All sorts of running out of room here. Keep getting an internet connection error, so I don't even know if I have an audience right now. 3.35e to the, golly, this problem is ridiculous. 1 plus 1.759e to the negative 0.0596 all over low squared. Holy moly. All right. It actually wasn't as bad as I played it out to be. It's just I have limited room on the screen, and I didn't want to have to put it onto a new page. But I mean, it's low d high minus high d low, and of course the low times derivative of the high. That's the derivative of the high is 0, so we don't have to do that. And then it's minus um, the derivative of the second part. Anyways, we want to find the rate at which revenue is growing in 2015. So we're going to do r prime of 2015 is 7 years after 2008. So we're just going to plug in a 7 for t. So this is going to be, oh my goodness, 3.35. Let's put that in parentheses times e raised to the negative 0.0596 times 7, and that's my numerator, divided by my denominator is 1 plus 1.1759 times e raised to the negative 0.0596 times 7, and then all that, well, let's say all that, but then that is going to be squared. Okay, let's make sure I'm right here. All right, well, I'm just trying to make sure my calculations are all right. Okay, so I'm going to end up with a value of 0.474. So this is R is in billions of dollars. So 47% of $1 billion is 470 million. So we are increasing at a revenue of $474 million per year. Now, this is in 2018. I bet Dish isn't doing as hot today nowadays because everybody's cutting the cord, right? I meant to snip this. So that we just did B. We're just going to snip the equation, or sorry, snip the graph, and we're also going to snip the explanation. Alrighty. So this is this is the graph that we see here of the Dish Network that they can expect to kind of top off at a certain value, and the value being 31.95, but we'll be growing growing pretty quickly until then. Right? And it says, explain why an unrestricted growth model is an inappropriate, but a logistic equation is appropriate to model this growth. So exponential is an inappropriate model because, well, I mean, there's only a certain amount of people that will watch TV, right? But a logistic is appropriate because, well, the same reason why there's only a certain amount of people. And which leads me to something else. This is, I was reading an article many months ago about how NASCAR is alienating their viewers. Politics aside, whatever, they are alienating their viewers because they're branching out and trying to get, different groups to watch NASCAR. Now the thing is, and the reason why it makes sense from their standpoint is because everybody that's going to watch NASCAR is already watching NASCAR, right? They don't have to worry about that. They're already going to watch NASCAR. However, what they're trying to do is bring in people that don't watch it. And so right now, NASCAR might say, hey, only 32 billion people will, or oh, not billion, right? Only 32 million people will watch NASCAR right now. Well, we need to bring in a different audience, an audience that doesn't typically watch NASCAR, and so they're trying to expand and grow, and that's why a logistic growth model is indeed appropriate for something like this. All right, last example, I think. I just want to check because this is the longest lecture I think we've had, isn't it? All right, so let's snip this. And I actually think I need to snip the thing above it too. Yeah. This goes here, and this goes here. Alrighty, so another model of limited growth is given by this equation, which is graphed below. This function increases over its domain 0 to infinity, but increases most rapidly at the beginning, unlike a logistic function. The differential equation dp over dt is equal to k times L, again the limiting population, minus p, which is the population, models a limited growth function in which L is the upper limit, again the limiting limit, well, yeah, limiting limit, that makes sense, of the population p, and the rate of change p is directly proportional only to the remaining room of the population growth, which makes sense. If you're only limited by, let's say your limit's 100 people in some dining area, right? And you have 80 people in there already. Well, you only have so much more room to grow. You can't fit more people into a dining area, right? The fire marshal won't allow it. So that makes logical sense. And so let's check out what we have here with the value of headphones. Alrighty, so a new model of Bluetooth capable headphones originally sells for $45 per set, and then 5 weeks later is selling for $52. Market analysts expect that the headphones will eventually sell for $70. Okay, so A reads, use the limited growth model, seen there, to find P of T, the value of the headphones after T weeks. So in order to figure out that equation, we need to find, well, let's just write it down and we'll see what we have to find, because this is one of those equations. So I'm just gonna rewrite the equation that's given to us. It says use the limited growth model. All right, so the equation is P of T is equal to L, which is my limiting, plus C e to the negative kt. And we want to find the value after t weeks. Okay, so in order to, let me fix this C up. C kind of looks a little weird. So in order to figure this out, we have a little bit of a problem here, right? We are given, let's again, just looking right here at this right side here. We are given a limiting value. Okay, again, E is not a variable, it is an actual number, it's just a number expressed as a letter. Right? But we don't have a C, we don't have a K, and we're asked to find T. This seems rather ridiculous, doesn't it? Because if we look at the previous problems, let's go back and look at some of the previous problems here. Maybe not that one. We are given, heck, where's it at? We are given in a lot of these. We're given the V naught. We had to find K. So we were given the constant, right? The C, but we weren't given the K. Or in one case, I think we had to find the K. Well, I know we did. I forgot which problem it was. Oh, in this case, we're given the initial value and the K. And for this one, we had to find the K. And for this last example, we are tasked with finding both the constant and the K. Well, lucky for us, we're given again, like I said before, the x, y value. We're kind of given that here in terms of they originally sell. So at the very onset, they sell for $45. So when t is equal to 0, they sell for $45. So we're going to use that to find k. Okay, so we're going to say at the beginning they sell for $45. Okay. Again, my limiting value here is $70 plus, well, we don't know what C is, and that's what we're trying to find out. C times e to the negative k, and then t in this particular case is 0. So that, unlike the problem I had earlier where I was trying to find k and I took it out, right? I multiplied k times 0, and it was like, we can't go this route. We're going to be doing the opposite here. We can't actually go this route because we're trying to find C. Well, negative k times 0 is just 0. E raised to the 0th power is 1. C times 1 is C. So my equation is just simply going to be something that looks like this. 45 is equal to 70 plus C. So if I subtract 70 from both sides, I end up with C is equal to a negative 25. Okay, so that's C. Now let's find T. So in order to find T, we're gonna kind of set up the problem the exact same way, except we're gonna use the other point, which is 5 weeks later they sell for 52. Okay. Again, I can't use the first one because I'm trying to solve for K, and I'll have that problem I ran into in an earlier example. So we're gonna say, well, 5 weeks later they sell for $52. That's equal to my limiting value plus C, which we said was negative 25, and let's just put negative. Let's just put minus 25. Let's not even put plus and negative. So minus 25 times e to the k times t, which we said was 5, right? 5 weeks later. And then we can solve for k. And well, let's just go and do this. So if we subtract 70 from both sides, we end up with a negative 18. We might have to go to the next page for this one. So negative 18 is equal to negative 25 e to the 5k. And if we divide both sides by, now we can do this. All right, so if we divide both sides by a negative 25, we end up with an 18 over 25, and that's equal to e to the 5k. We're going to take the natural log of both sides, and we're going to end up with, and put this right up here. We'll have the natural log of 18 over 25, and that's equal to, we know that the natural log of e to the 5k is just simply 5k. Sorry, it's supposed to be a negative in there. Negative, 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 negative. Negative 5k. And then if I divide both sides by negative 5, then I get k is equal to, so the natural log of 18 divided by 25, and then it's divided by negative 5. So I get 0.0657. Whew, okay, so model to find P of T, the value. Okay, so that kind of wraps up A. Let's go ahead and snip this problem again and put all that together because we had to find C and we had to find K. So A is now officially P of T is equal to my limiting growth minus 20 minus 25, 0, 0.657. 0.657. T. Okay, hopefully. All right, I think that sounds right. 0.0657 and then times T. Okay, so finally we're done with A. That's kind of unusual. Usually A is the easier, quicker one. Yes. Alrighty, so that's A. B, find P prime of 15. So all we have to do is differentiate this and plug 15 in for T. Well, P prime is going to be, all right, well, 70 doesn't matter, and so I'm just going to take the derivative of this second part here, and that gets me 0.0657 times 25. So we're going to end up with a positive 1.6425 that's P prime. And then P prime of, what do we say, 15 is equal to, we plug 15 in for T. Oh my goodness, okay, so we get 0.613. Okay. And then lastly, when will the value of the headphones be $65? And this deserves its own page as well. So let's do that. With that said, this particular lecture, it's already going on an hour and 11 minutes. I find the value in recording lectures a lot better than sitting in a classroom, because in a classroom, I bet, in fact, I've already lost one student. Oh, I've lost two students already. So sitting in a classroom, I bet many people check out after 10 or 15 minutes, much less an hour and 10 minutes. So being able to watch this on YouTube is pretty valuable. Anyway, so when will the value of the headphones be $65? What we need to do is we need to look at our equation over here, the equation that's written in the green. So we need to figure out when the value is $65. So we need to figure out this side. We're going to put 65 here, and we're going to solve for t, right? Because p of t is the price. So when will it sell for $65? We want to know how many weeks later. So I'm going to have to use that equation. So let's go ahead and write this equation as, I forgot, so 70 p of t is equal to 70 minus, I think it was minus 25 times e to the negative 0.0657t. I think that's right. I think that's right. Okay. So I have to figure out, I have to plug in a 65 in for p of t. So we'll have 65 is equal to 70 minus 25 e to the negative 0.0657t. So let's go ahead and do two things at once here. Let's go ahead and subtract 70 from both sides. So we end up with a negative 5 on the left. We're going to divide both sides by negative 25. So it's going to be a positive 5 over 25, or positive 0.2. So 0.2 is equal to e to the negative 0.0657t. We're going to take the natural logs of both sides, so we end up with the natural log of 0.2 is equal to, if I take the natural log of the right side, it just becomes negative 0.0657t. And then we're going to divide both sides by negative 0.0657t, so we end up with t is equal to the natural log of 2 divided by negative 0.0657. So 24.49, so 25, so 24 and a half weeks, so 24.5. So the value of the headphones will be $65 when t is equal to 24.5, or in 24 and a half weeks. Okay, and last but certainly not least, the section summary. So if you happen to watch this video all in one sitting, good for you. I myself teaching this have gotten bored to tears. But that does conclude today's lecture.